All right. So as we were saying, we are saying that a compound bar consists of a compound bar consists of a circular rod of steel of 25 diameter, rigidly fixed into a copper tube of internal diameter, let's say 22 millimeter, and external diameter 40 millimeter, as shown in the figure below. It means that the copper tube is the hollow one. Do you understand me? So this can be the copper tube as you are seeing over here. This is the copper tube as you are seeing over here. It's just a hollow copper tube. It's just a hollow copper tube. It's just anyone should continue, someone to continue to read the question for me. I want someone to continue to read the question for me. So this is how the copper tube look like. Okay, this is the copper tube. So the copper tube is a hollow one. Okay, exactly. And let's say that the internal diameter, okay, that is, it could be from here to here. The internal diameter is what? This one. The internal diameter, this one. So I will name it DI to show you that it is just the internal diameter. Okay. And then the bigger diameter, let me use a different pen to denote that. This is the bigger diameter. The bigger diameter is just actually the, you see, the end of one circumference to the other circumference of the bigger circle. Okay. So I can denote the bigger diameter to as what? This is the what? External diameter. Okay, so if I write D, it means the external diameter. So the inner diameter is 25 and then the external diameter is 40 millimeter, as shown in the figure below. If the compound bar is subjected to a load of 120 kilonewton, if the compound bar is subjected to a load of 120 kilonewton, find the stresses developed in the material. Okay. If the compound bar is subjected to a load of 120 kilonewton, find the stresses developed in the two materials. So at the end of the day, we are supposed to find the what? Stress in what? Material one. Okay. We don't know. We are also supposed to calculate for the stress in what? Material what? Two. Okay. That's one, so we don't what? No. Okay. So at the end of the day, the elasticity of the steel is 2 times 10 exponent 5 Newton per millimeter squared, and then the elasticity of our copper is also 1.2 times 10 exponent 5 Newton per millimeter squared. Okay. So at the end of the day, this is the hot steel rod, and the steel rod has been placed in the hot hollow copper tube, you see, to form a composite section. So we just have to use the conditions. Okay, that is, we said that to be able to solve a composite section question, you have to what? Or the criteria such as compatibility condition and also equilibrium conditions must be met. If they are not met, it means that whatever we are going to do is just going to be cos 90. Okay. Yes. So at the end of the day, we are saying that for compatibility conditions, the load of material one, okay, or let me say the sum of the load of the materials, that is, it could be one and two, should always be equal to the total load. Okay. Should always be equal to the total load for the equilibrium condition. But for the compatibility condition, the change in length of material one should always be equal to the whole change in length of the material two. Take note that it's in most cases it's not just two materials, it could be three or even more. Exactly. So let's just share a different screen and see how we can be able to solve our problem to make life much more easier. But at the end of the day, these are the answers we are expected to get. If we are not able to get this answer, it means that whatever we have been solving, it is wrong. Okay, so this is what we have to be chasing for. That is the stress in material hot. Or let me say our stress of the steel, we are supposed to get 126.25 Newton per millimeter squared. And also the stress of the copper, in the copper, we are supposed to get 75.78 Newton per millimeter squared. Okay, without talking much, let me just share a different screen. Let's begin from the given and see how best we can be able to proceed. So this is our given. This is our given. Okay, so please, I want someone to read the question one last more time again for me. I want each and every one of us to take a screenshot of the question. Quickly take a screenshot. Quickly take a screenshot of the question before we proceed. We are just going to write the given and then we proceed. Okay. So if you are done taking the screenshot, I'm going to share a different page and then I want someone to read the question for me so that we can write down the given. Okay. So can someone read a question for me? All right. Our question says that a compound bar consists of a circular rod of steel, 25 mm diameter. Okay. So let's say the diameter of steel. So the diameter of steel, the diameter of our steel, okay, we can denote it as just ds, okay, is equal to 25 mm, 25 millimeters, exactly. A compound bar consists of a circular rod of steel of 25 mm diameter rigidly fixed into a copper tube of internal diameter. Okay, so let's write that uh, this is the diameter of what? Uh, Inner diameter of inner copper tube. Okay, so the diameter of the inner copper, let's is equal to let's denote it as di. Okay, so it's equal to uh 25. Let's quickly check it again. 25 mm. Okay, so that is 25 mm. Okay, and then the diameter of, let's say, outer copper tube, and the diameter of the outer copper tube is equal to, let's say we can denote it as what? Do. Okay, so, and that is equal to 40 millimeters. 40 millimeters, exactly, exactly, as shown in the figure below. So this is it that we are seeing over here. This is it shown in this figure as we are all seeing over here. Mhm. If the compound bar is subjected to a load of 120 kilonewton, so let's say the load in tension. So let's say the load, this is the load in tension. So the load in tension, the load in tension, we can denote it as what? PT is equal to 120 kilonewton. Okay, which is just the same as 120 times 10 exponent 3. 120 times 10 exponent 3 Newton. Okay, don't get confused. So finally, we are saying that find this. If they say we should find the stresses developed in the two materials, take the elasticity of the steel to be this and elasticity of copper to be that. So let's quickly go and put that down. So elasticity, that is elasticity of steel. So let's put that down. Elasticity of steel is elasticity of steel. So elasticity of steel can be denoted as what? ES. Okay. And let's also put down the elasticity of copper. So elasticity of copper is equal to what? EC. Okay. So let's quickly put them down. And the elasticity of steel is equal to 2 times, let's say, 10 exponent 5 Newton per millimeter squared. That is Newton per millimeter squared. Exactly. Also, the elasticity of copper is equal to 1.2. Okay. Times 10 exponent 5. Okay. Exactly. Newton per millimeter squared. They are all the same thing. Don't get confused. They are all the same thing. Don't get confused. Okay, exactly. So we are done putting down our given. Whatever you are seeing over there, this is what I have. I'm just going to put down my diagram. I'm going to put down my diagram to get more marks. So you don't have to lose that mark. Okay. So this is the diagram I'm going to put down to represent the question. This is the diagram I'm going to put down to represent the question. So I'm going to shade inside the first one just as they have done over here. You see. So let's shade it together. Let's shade it together. At this point, good students should take a pen and a paper, an eraser, a calculator, so that they can also be able to do whatever we are doing. Okay, you should also be able to do whatever we are doing. As I'm writing, you should also be writing. This is something that we are doing. It's very, very practical. If you don't involve yourself, you realize that at the end of the day, you are going to confuse yourself. Okay, so it is now or never. You have to fly now or never. Yes, procrastination is never the best. Exactly. So this is the copper section, and then I want to shade inside a different color to indicate the steel section. Okay, so this is the steel section that is being placed in it. This is the steel section that is being placed in it. You can see that I'm shading it. It's a different color. Yes, as simple as that. So this over here is the steel. Okay, this is the steel, and now this is become the copper. So this is the copper tube. This is the copper tube. Exactly. Exactly. And now this is our steel rod. Steel rod. Okay. This is our steel rod. This is our steel rod. So this is all what I've been talking about. We have been able to put down our given. Okay. So we can just uh, proceed by solving our questions, and then we can start making history. At this point, is anyone having any question to ask before we proceed? You can just punch your comments you can just type your answer in the comment section. I'll review it and give you a feedback just as others are doing. Exactly. Okay. So let's continue with our solution. Okay. Let's continue with our solution. Let's continue from our solution. So this is what we were given. Okay. So we want to continue from our solution. So let me write the solution over here. This is our solution. So this is my solution. Okay. So what did we leave out? One thing we left out is that our stress was unknown. Let me say that the stress of steel. Okay. The stress in steel. So the stress in steel, we don't know. The stress in steel. The stress in steel rod. Okay. Is equal to this. I would just denote it as this. And it is what? Unknown. Question mark. We don't know. That is what we are going to be looking for. And also the stress in copper tube. Okay. The stress in copper tube is also unknown. The stress in our copper tube, that is stress in our copper tube, is also what? Unknown. So we can now proceed. Okay, let's continue with our solution. Let's continue with our solution. So, but before then, we said that what? Let P is equal to load of steel and PC is equal to load of copper. Okay. So let's make some clarification before we continue. So before then, we are saying that what? Let PC is equal to load on steel. Let PC is equal to load on steel. And also let what let's this is supposed to be PS. Okay. So let PS is equal to the load on steel. And also let's let PC to be load on copper. So this is equal to the load on copper. Exactly. And let's put over here the stress in copper. This is the stress of copper. Okay. So let's put over here. This is the stress of copper. The stress of copper. Then this is going to become our stress of what? Steel. So you can take note of some of these things. This is just going to become our stress of steel. The stress of steel. Just as you have seen, I've written this already, but I'm still writing it again. Okay, so let's proceed. Let's proceed. Let's proceed. Let's proceed. So this is also the steel rod. Okay. Mm, This is also the steel rod. So we are just going to proceed from our step one. Okay, so we want to group our calculation into steps. Okay, so let's say for our step one, from our step one, from our step one, we are going to be calculating for the area. Okay, from our step one, we are going to be calculating for the area. Okay, so let's quickly calculate for the area in our step one. So I'm going to draw a nice line. And we are going to write calculation for area. So we are going to do calculation of areas. Okay. So this is going to be calculation of areas. So this is calculation of areas. Calculation of areas. Okay. If I say calculation of areas, I'm actually talking about, let's say, the area of the steel rod and let me say the area of the hot copper tube. Don't get confused. So first of all, let's take the area of steel rod and let's calculate for it. Then we can also take the other one and calculate for it. Okay. So this is the area of the steel rod. Let me write over here area of steel rod. So we want to first calculate for the area of the steel rod. So let's first calculate for area of steel rod. Area of steel rod. And then the area of steel rod, we can denote it as what? AS. The area of steel rod can also be denoted as the AS. AS. As beautiful as that. So for the area of the steel rod, it's just a solid one. And we realize that since it's a solid one, we can use our initial formula we have been using. That is our A is equal to any circular tool. So it's going to be what? Pi d squared over 4. Okay. Pi d squared. Pi d squared all over what? 4. Okay. So by substitution, we can just substitute our values into this and then we can find for our area. Okay, and that is the pi we are using over here is just 3.142. So that is 3.142. Okay. All over 4. Okay. all over 4. Then what is in the bracket is D. Let's put it into the bracket. It's 25, right? So we put 25 over here, 25 millimeter, because that was the diameter of the steel rod. Okay, all this one is squared. So quickly punch that in your calculator. Everybody, please, let's all do that together and see the answer we are going to get. So for the area of our, we are going to get 490.3975. I'm sure that is the answer we are going to get. When you get the answer, just punch the answer into the comment sections, and then I'll review that for you. As simple as ABC. Okay. You are going to get 490.9375. Okay. So this is it. Millimeters squared. Four 90.9375. Okay. Yes, millimeter squared. Okay. Exactly. Exactly. So I can see some comments in the comment section, and that is so wonderful. Okay. So in our conclusion, we can conclude to say that what? Therefore, our area of what still, okay, that is AS, is equal to 490.9375 millimeter squared. Okay, as simple as that. So let's also come and calculate for the area of what? Hollow copper, okay, tube, because it is a hollow one. So let's quickly do that too, then we can proceed, because you know that without the area too, we cannot move. So we have to do first things first. Okay, so this is the area of hollow copper tube. Area of hollow copper tube. Area of hollow copper tube. Okay, so area of copper tube, or if you like, so you can just say that area of copper tube. It is also still accepted. Okay, don't get confused. So this is can also be written as just area of the copper tube, and I can denote it as what? AC. That is the area of the copper tube. Exactly. So the area of the copper tube, because it's a hollow one, this is the formula we are going to be using, and our area is going to be equal to, or let's say the area of our copper tube is going to be equal to pi. Okay, it's still pi d squared over 4, but because this time it is hollow, we have to subtract the what? Smaller diameter from the bigger diameter. Okay, so that is going to be now expressed as what? This. Okay, or let me say all of this multiplying, let me put this into brackets, the d o, okay, minus what? The di. Okay, or let me say better still, this one squared and also this one squared. So this is the formula that we are going to be using to calculate for it. Okay, so by substitution, let's quickly do that together and see how best we can be able to proceed. Okay, better still, this can also be written in this form perfectly like this. Yes, for punching purposes, let me write this. Let me write this in a more nicer way, so that when you are punching, you know how you punch them accurately. Okay, so this can be what? D, that is the outer diameter. Okay, then you square all of this minus what? That of the what? Inner diameter. Okay, then you also square all of this. As simple as that. This is all the formula. Okay, so by substitution, let's just substitute our parameters into the equation and see the answer we can derive. So this is going to be equal to what? 3.142 all over 4. Okay. Times. Now we can say that the outer diameter was 40 millimeters. Okay. 40 millimeters all squared minus the inner diameter was 25 millimeter. 25 millimeter to, let's say, all squared. So finally, the only thing we are going to do is that we have to punch this into the calculator, and now we can get our answer. Okay. So you see that therefore the area of our copper tube is equal to this. Okay. So everybody, let's quickly point this together. Let's quickly point this together. That is 3.142 all over 4. Okay. Times bracket open, the outer diameter all squared. Okay. Minus the inner diameter to put it into brackets. Okay. After that, close the bracket, square it, you can close the big bracket. And you realize they are going to get 765.8625 millimeter squared. That is what? 765.8625 millimeter squared. So this is our area for the hot copper tube. Okay. So the area for the copper tube, this is what we have gotten. This is what we have gotten for the area of the copper tube. Okay. So let's proceed. Let's proceed to our step 2. Let's proceed to step 2 of our solution. Let's proceed to step 2 of our solution. So this is our step 2. So in step 1, we calculated for the area. You see, now in step 2, we are going to be doing equilibrium condition. Is it not beautiful? So we are going to be doing for equilibrium condition. Okay, just as we did for the previous one, we're going to be doing the same thing. Okay, so we want to first start with the equilibrium condition. So let me write it. This is equilibrium condition. Okay, so this is equilibrium condition. So this is equilibrium condition. Equilibrium condition. If you say something is equilibrium, it is actually stable. Okay, if you are not equilibrium, then it means that you are not stable. So equilibrium condition. Equilibrium condition. So the equilibrium condition is that the load of material 1, okay, the load in material 1, okay, the load in material 1 plus the load in material 2 should be equal to the total load, okay, in tension. So we can just denote it as this. That is the load in hot, the steel plus the hot. The load in copper is equal to the hot total load, okay, which we are saying that it is in hot tension. So we can just even denote this as our equation 1. Let me just denote this as equation 1 for you. Take note of this equilibrium condition. I'll come back to refer to it again. Okay. But from past relations, we are saying that what? But from whatever we have been learning so far, we are saying that but, comma, okay. So that is but P, okay, that is our load, is equal to stress times strain, which I have explained to you already. Is equal to the stress times the area. Okay. But our load is equal to the stress times the area. Okay. But our load is equal to stress times the area. Okay, so from substitution, we can rewrite that as we are seeing over here. Okay, so we can write it in terms of the equilibrium condition, and look at that. This is how that is going to now become. So it is going to become something like this. Okay, it is going to become something like this, and that is, let's say that for the first one, for PS, we can write it in this form. Okay, stress of what? Still. Okay, times, if you see dot, it means times. Okay, the area of what? Still. You see. Then what else are we bringing? We can now bring our plus, right? So they said that plus what? PC. So for the PC, when I bring my plus over, I can also bring plus over here. Okay. And now for the PC, to I'll write it as what? The stress in the what? C. Okay. Times the area of the copper. Okay. Times the area of the copper. Then finally, is equal to what? The total load. The PT we are talking about. Okay. So we don't know it. So at the end of the day, we just have to put what? PT over here. Okay. And this is still the equation one I spoke to you about. Okay, I'm just trying to relate it to just show you something. It's not anything strange. And so if that is the case, I'll just have to cover it again. I'll just have to cover it again. Okay. So let's proceed to solve our problem. You see, so that is what we are saying. Okay. So if that is the case, if we want to substitute our parameters, because we have already calculated for the area of copper and steel, let's quickly put it for it inside and see how we can establish equation 2. Okay. So we don't know the steel, we don't know the formula for the, so we have to just express this as this. We don't know this. This is still what we are looking for, but the area we know. But the area of the steel we had 490. Okay. So let's put it over there. That is in place of this. We can write that